Thank you very much. And this kind of a neat slide that actually is a picture of me taken by Drew Feustel as I was repairing the Hubble Space Telescope. And as Chris Scalise said, I started out life, I'm not going to tell you the long story, but as a high-energy astrophysicist, and I was just fascinated by black holes, neutron stars. My first scientific paper was an observation of a neutron star, a star the size of Washington, D.C., rotating rapidly with the density of nuclear matter, and went on to build balloon payloads and do experiments and work with space experiments, including the Compton Observatory, that I was convinced was going to be my career. And I looked very jealously at the Hubble Space Telescope, thinking, it's just an optical telescope. It's taking all the money. The real action is in high-energy astrophysics. But I think we should all be continuous learners, and I learned how important Hubble is, and the next speaker will refer to that. And in fact, I became actually quite transformed by the Hubble Space Telescope. But I also became transformed by the fact that when the Compton Observatory was on the end of the robotic arm, the high-gain antenna didn't deploy. And it was Jerry Ross and JF went out and did a spacewalk and deployed it, enabling my research and many of the folks that are in this room to be able to unravel the mysteries of the universe, the high-energy universe with Compton. And we're going to hear more about some of the follow-on great spacecraft and experiments and the science. But it really comes down to what NASA is all about. We innovate, we explore, we discover, and we inspire. And we innovate to build the kind of technologies that allow us to build spacecraft like NuSTAR, which you'll hear about. We use those innovations to explore the universe. And when we explore, we discover things. And that's where the human element is at its strongest. We're driven, I think we're genetically programmed to be energized by those discoveries. And when we're energized as scientists, we're able to inspire a country, a world, students, everyone. And I think that's the importance of the science that we do. We're also asking human questions, in essence. We're asking fundamental physics questions, science questions, but we're trying to find out, where did we come from? Where did the universe that we live in come from, and why does it look the way that it does? Where do the chemical elements that we're made out of come from? And it turns out they came from a very violent universe, and we'll hear hopefully a little bit about that. We're made out of star stuff that had to get from the inside of stars out of stars to form new stars, planets, and us. Where are we going? What's the future of the universe? That's also dominated by high-energy processes, but also where are we going on planet Earth? That's one of the things that we do in Earth science. And then the big question, which I don't think high-energy astrophysics is going to answer, but one I'm fascinated by, is are we alone? And that's why some of our planetary missions and our exoplanet missions, I think, are so interesting now, because we are one step away from having the technological capability to answer the question through telescopic observation of nearby exoplanets, interrogating their atmospheres to find out if we're alone in the universe, or a future planetary scientist, and there's some young people in the audience that are those future planetary scientists who are going to walk on the surface of Mars with analytic tools that may be able to tell us whether there's life on Mars, or a planetary mission exploring Europa. So this is one of my favorite events because every year we get to hear about the great science that's going on at the Goddard Space Flight Center and through it, its participating scientists, and really learn something important. And so what I'd like to do in my final comment tonight is address the inspire part of our mission, which is to ask all of you tonight after you leave, drive safely going home, but tomorrow and the next day and for really hopefully the rest of your lives, as you learn about our great scientific achievements, as you yourselves, discover things, share it with your neighbors. Certainly share it with your family members. Many of us go to work in the science community. We work really hard. We come home, we're tired. We have a meal, we go to sleep, and we don't tell our families about the great work and incredible work we're doing, studying the environment around a black hole or a rotating neutron star or an active galactic nuclei. And it really is amazing. People are amazed by what we do. Share it with your community groups, share it with local schools, because it's through that communication that we inspire the world. So I hope you're all inspired tonight, and I was inspired when I was a high school student. I like to say everything I learned about astronomy I learned as a high school student in a program at a small planetarium in Chicago called the Adler Planetarium. And one of the graduate assistants that was teaching us was somebody who has throughout my career become a mentor, and was my predecessor. And so I'd like to bring up Dr. Ed Weiler to give us an introduction.
Thanks, John. I'm really not that old. But I am retired, if you've wondered where I've been the last 4 years. But when you're retired, you have lots of time, finally, especially between tennis matches, to gain perspective on what's happened in your field of astrophysics over the past 40 years. That's how long my career has been. Back in the 70s and 80s, when many of us were in grad school or just starting college, we thought we knew a lot about the universe. We were pretty arrogant. We kind of knew how stars were formed and how their atmospheres worked, etc. But there were some awfully big problems left unsolved which were nagging at us. And those are the ones we'll be addressing, some of them, tonight. For instance, do supermassive black holes really exist? Or are they just mere science fiction and fodder for shows like Star Trek? What are quasi-stellar objects, quasars? They appear as pinpoints of light in the sky, but extremely distant and thus very energetic. Some are relatively quiet, while others seem highly variable. Do they have homes in the universe, or are they solitary objects in the vast darkness? In the early 80s, diffuse X-ray background was discovered to fill the nighttime sky. What was it? Gamma ray bursts were seen almost once a day. They last very short periods of time, seconds or up to a day. Are they nearby or extremely distant and thus very energetic? And finally, we think supernovae, back in the 80s, we knew supernovae were probably violent explosions, but what was their exact nature? We know that they created elements in our bodies, calcium, iron, etc. And thus it was important to better understand these violent phenomena. It was recognized by many back then to tackle this broad array of mysteries, it would take large space observatories operated in multiple wavelength bands from gamma ray to infrared. And soon we'll see. You'll hear the term wavelength tonight perhaps. Think of wavelength as colors. Our eyes can only see in this little area of visible light here. If you want to look in the ultraviolet, X-ray, gamma ray, much of the infrared, you have to go into space to see basically the rest of the universe. I remember after we sold Hubble, we were trying to sell Gamma Ray Observatory and SERTIV and AXAF, and one congressional staffer, who shall remain unnamed, came up to me and said, hey, you guys are getting Hubble, we're paying a lot for Hubble, why in the world do you need all these other observatories? And I'll use the analogy I used that day with him, and I said, well, if you had a really bad disease and you went to the doctor to get diagnosed, would you go to a doctor who basically used their eyes and their hands to diagnose you? Or would you prefer a doctor that might use state-of-the-art technology like MRIs, CAT scanners, stethoscopes even, ultrasounds? And astronomers are in the same boat. If you really want to understand a lot of objects in the universe, you've got to look at all wavelength areas, because these wavelength areas really tell you about the temperature of the matter in the object. Gamma rays and X-rays, tens of millions, hundreds of millions of degrees, ultraviolet, hundreds of thousands of degrees, visible light, tens of thousands of degrees, infrared, hundreds of degrees. So if you want to understand an object, you really have to look at it in many, many different ways. An example of multispectral imaging is displayed in the next two images that will be coming up. On the left here is a Hubble image of Cassiopeia A. It's a result of a supernova that happened a long time ago. Supernova occurred here, and what you're seeing now is the leftovers of the supernova glowing at about 10,000, 20,000 degrees. And until we launched X-ray telescopes, that's as much as we saw. This is a Chandra image here on the right. Let's see, you're right. As you can see, this is now showing us million-degree gas, tens of millions of degree gas, and you can see the very big difference in structure. You learn unique things by looking at different wavelengths and a different temperature of objects. In the early 1980s, the Great Observatory Program was created by Dr. Charlie Pellerin. He was a visionary at headquarters who realized it would be difficult to sell individual flagship missions that covered the whole spectrum from gamma ray to infrared. So he created a scientifically driven program that included the already funded Hubble and Compton missions and the AXAF and SERTIV missions that were under study. He was obviously successful, and the early discoveries from these observatories allowed us to launch follow-on missions that you'll hear about tonight, such as Fermi, Swift, and NuSTAR, to name a few. Now for the rest of the evening, we'll be describing the progress we have made over the past 30 years in tackling some of the questions I've just discussed in our violent universe. I hope that we will convince you that the last 30 years, 3 decades, have truly been an age of discovery and an astrophysical renaissance. I will discuss briefly 3 major breakthroughs, including the existence of supermassive black holes, the nature of quasars and their power source, and the nature of diffuse X-ray background. Jeremy will follow me with a more detailed look into the nature of black holes. Fiona will discuss supernova explosions and their aftermath, and Neil will conclude by telling us how far we've come in understanding mysterious gamma-ray bursts. First, one of the most intriguing mysteries of astrophysics, especially back in the 70s and 80s, do supermassive black holes exist? And actually, that question came to an abrupt end in 1994 when some of the first images from the repaired Hubble telescope came back. This is the galaxy M87 here. You see the radio jet. And for the first time, we were able to image the gas, hot gas, going around the central object. And we were able to measure the velocities with the faint object spectrograph. And literally using high school math, you could determine, knowing the distance of M87, knowing the velocity of the gas, knowing the scale of this picture, you were able to very quickly discover that within a volume of less than a solar system, there were 3 billion times the mass of the sun. Einstein was right, because nothing that dense can be anything but a black hole. This one observation basically put to an end the discussion of whether black holes existed or not. Okay. Over the following years, more discoveries were made by various space observatories that demonstrated that not only did supermassive black holes exist, but they may be at the core of every galaxy, even our own Milky Way. Here we have a black hole going through space, then an unsuspecting star. This, by the way, this is an artist rendition. An unsuspecting star gets a little too close, gets caught up in the web of gravity, starts getting torn apart, creates an accretion disk of hot gas and dust rotating rapidly around the black hole. Black holes, contrary to popular belief, they're not the ultimate Roach Motel. They don't eat everything. They're very messy eaters. They eat and they're very, very messy. You've got tremendous magnetic fields created by the rapidly rotating charged particles here, which create magnetic fields, and some of the matter that doesn't get trapped in gets shot out in jets. This is, the closer you get to a black hole, the temperatures get hotter and hotter. If you really want to study the inner parts of the accretion disk, you have to look in the gamma rays, X-rays, because you're talking about gas that's 10 millions or more degrees. And the outer portions of the ring of the accretion disk are a little cooler. But what we discovered here was the actual power source of quasars. This is what powers quasars, actively eating black holes. The quiescent quasars are quiet eaters, not eating too much at a time, and the active quasars that are highly variable are probably consuming at a high rate. Now the stage is set for the next mystery. Are quasars the homeless citizens of our universe, or are they an integral part of some larger structures? My friend and colleague from Princeton, when I was at Princeton, was John Bacall, and he was looking forward to using Hubble because his theory was that quasars were really in galaxies, that quasars weren't homeless, so to speak, that they lived in galaxies. And indeed, with Hubble imaging capability, this is a Hubble image. This is a radio jet coming out of this galaxy, and zooming in on the center of the galaxy with Hubble, we see the accretion disk, and we see what looks like a black hole. So John was right, and subsequent observations have shown that all quasars seem to be have a home in some galaxy at their center, and that the power source is probably a supermassive black hole. The last mystery that I'll be addressing is that of the cosmic soft X-ray background. Back in the 80s, I said low resolution. The first X-ray satellites saw this fuzz in the universe, low energy X-rays. My analogy here is if I gave all of you a candle and you held it up, right now I wouldn't see individual lights, I'd just see a fuzz because my glasses are off. Right? If I put my glasses on, 20/20 vision, suddenly I'd see it's not a fuzz, it's all individual candles. And that's exactly what happened here. The early satellites didn't have the resolution. This is a Chandra image that showed this fuzz was actually created by thousands, if not hundreds of thousands of point sources. In fact, this little area, these 5 objects here in the Chandra image, match up beautifully with galaxies in the Hubble Deep Field. As it turns out, about 80% of this background, these individual sources, turn out to be quasars. Another mystery solved. Now I'd like to wrap up by getting a bit philosophical, if I could. I've talked about several long-standing mysteries that have been solved over the past 30 years, but the universe is a very, very big place. This is the deepest image of the sky ever obtained, the Hubble Ultra Deep Field. There are over 10,000 galaxies in this one image. Some of the galaxies are so far away they're only babies, as they appeared 13 billion years ago, 700 million years after the universe was born. Yet the image is only 1/40,000,000th of the sky. In other words, it would take 40 million Hubble Ultra Deep Fields to cover the entire sky. If you wanted a human analogy, go out on a clear night, get a standard sewing needle, hold it up at arm's length, and look at a hole in the sewing needle. That's the size of the sky you're seeing portrayed here. So despite all the mysteries we have solved, let's not get too arrogant. As I said, the universe is a very, very big place, and there's a wee bit of work to be done. If this makes you feel small, it should. We humans, after all, have only been around for about 100,000 years on a planet that's been here for 4 billion years or so. We live on a small rock called the Earth, which orbits a routine star called the Sun. And the Sun is one of hundreds of billions of stars in our galaxy. And sorry, our galaxy isn't really special. It's just one of hundreds of billions of galaxies. But before you get too depressed, on the positive side, we mere humans, just in the past 30 years, have built space observatories which have enabled our minds and our spirits to travel any place in this vast universe and experience some of the most violent phenomena imaginable. Places our physical bodies can never go. And now, speaking about places your body should avoid, our next speaker, Jeremy, will take us on a much more detailed journey through the world of black holes.
Thank you, Ed, for that wonderful introduction. I'd like to just start with a personal request to all the students in the room that were mentioned earlier. If you see anything or hear anything that piques your curiosity in my talk tonight, please, please don't hesitate. Look up my email. I'm the only Jeremy Schnittman in the world. Send me an email and ask me your question. I'd be happy to talk to you more. Even better, next time you're at Goddard, just stop by my office. So as Ed mentioned, I'm going to talk about black holes tonight. So let's start with the basics. What exactly is a black hole? So just like Sauron in his dark tower, black holes are known for being terrifying, invisible sources of death and destruction, much feared but little understood, far off in the land of shadows, veiled in an impenetrable cloak of mystery. Well, I'm afraid I've got some disappointing news for you. Black holes are actually boring. There is literally nothing to them. Now, the cosmic web of galaxies is intricate and beautiful. Stars are sources of twinkling wonder. Planets are graceful and majestic. But black holes are black. Let's zoom in for a closer look, please. Still boring. It's really only when we zoom out and see the black hole in the context of its surrounding environment do we begin to appreciate how they might not be so boring after all. Truly, it's the stuff around black holes that makes them so interesting. And when this stuff is gas, it usually forms something called an accretion disk, like Ed mentioned. What we're watching here is an artist's impression of what an accretion disk would look like close up. Now that is beautiful. And while I admit I am certainly biased on the subject, I can't help but think that the astrophysicist's impression of an accretion disk is even more beautiful. Black holes are such powerful gravitational monsters that they warp and twist the very fabric of space-time itself around them. They can actually bend light, leading to images like this of an accretion disk simultaneously viewed from above and below. We can even see an inner ring caused by light that goes all the way around the black hole before escaping and eventually making it to us. I could watch this movie for hours. It's more peaceful than terrifying. And the truth is, just like a vortex in a pool of water, black holes really aren't that dangerous unless you get extremely close to them. And in practice, it's really very difficult to get close to a black hole. Why? Because for the same reason that planets just go round and round the sun without ever getting sucked in, because of angular momentum. So gas orbiting around a black hole can never actually reach the event horizon unless it first sheds its angular momentum. And it turns out this is quite difficult to do if it doesn't have anything to push off of. If you were a blob of gas orbiting around a black hole at half the speed of light, I mean, what would you push off of? I suggest we could actually learn from roller derby. There's a maneuver called the whip. And the skater on the inside track starts off by going faster, and then she whips her partner around, transferring angular momentum outwards. Afterwards, the inner skater is going slower, and if she were orbiting a black hole, is one step closer to getting sucked in. Around real black holes, magnetic fields take the role of the whippers, pulling some gas in and throwing the rest out into space. Again, like Ed mentioned, they're messy eaters. In the accretion disk, the gas is threaded with this complex turbulent network of magnetic fields, constantly getting twisted and wrapped around like rubber bands. And just like rubber bands, these magnetic fields can stretch until the point where they snap, releasing massive amounts of energy, heating the gas to millions or even billions of degrees, just like in the corona of our sun. Now, this superheated gas shines very brightly in X-rays, which is exactly why we like to use telescopes like Chandra and NuSTAR to study black holes. Now, accretion disks aren't the only way that you can study this curved space around black holes. One of the remarkable predictions of Einstein's theory of relativity is that space-time is not only curved, but it's also twisted. In this computer simulation of particles plunging into a black hole, we can see this effect of the twisting of space-time most prominently right outside of the event horizon, where particles are being swept around in a counterclockwise swirl at nearly the speed of light. We're watching nature's own particle collider in action here, a furious maelstrom generating higher energy photons called gamma rays. Now, altogether, the pulling, the twisting, the slinging, the whipping of gas by the black hole leads to tremendous high energy particles and relativistic jets, both of which can be seen with telescopes that look in the X-rays and gamma rays. Now, to conclude, I would like to observe that this year does mark the 100th anniversary of Einstein's theory of general relativity. And we're just beginning to scratch the surface of what this remarkable theory predicts. We look forward to the next 100 years of finding and conquering the beasts of the cosmos. And now to tell us exactly how you find these beasts and tame them with the NuSTAR telescope is Dr. Fiona Harrison. Thank you.
Okay, thanks, Jeremy. So I'm going to tell you about discoveries from the NuSTAR mission, which is the first real telescope to look at the universe in high energy or blue X-rays. So visible light is made up of a rainbow of colors, and so is X-ray light. This is a Hubble Space Telescope image of the nearby galaxy Messier 82, seen in black and white. We get much more information when we look at astronomical objects in different colors, when we get information about how hot, dusty, and energetic different regions are. Making an analogy with a visible portion of the electromagnetic spectrum. Before New Star, we could only make crisp pictures of the universe in red, orange, and yellow X-ray light. This is what M82 would look like if you could only see it in red, orange, and yellow, invisible. Mostly what you're seeing here is dusty, warm regions. When you add the blue to M82, the blue highlights hot regions where stars are actively forming. So New Star has added blue, indigo, and violet to the X-ray palette. This is bringing a richness to our view of the energetic universe that we've never had. It's like being an artist that has a full set of paints to work with. So, how did we add these colors to the X-ray band? Well, it was by making a new kind of telescope to image blue X-rays, going from a pinhole camera technology to a real focusing telescope. Now we can paint the high-energy X-ray sky in its full glory. Using the same energy or color X-rays that your doctor and dentists use to X-ray your body, New Star observes some of the hottest, densest, and most energetic regions in the universe. Because high-energy X-rays probe through your skin, they also probe through dust and gas in the universe, illuminating objects that would otherwise be hidden from our view. By employing new technologies developed over many years, on a small mission, New Star is making images that are hundreds of times deeper and crisper than previous high-energy missions that were 10 times the cost and size. So New Star is a small explorer. This is the smallest scale standalone astrophysics mission that NASA supports, and so it has to launch on a small rocket. New Star was attached to the belly of an L-1011 aircraft and launched into space on a small rocket called a Pegasus. There's not much room for the payload, which has to be a small fraction of the length of the airplane. So the problem here is that X-ray telescopes are inherently big, usually the length of a school bus. The way New Star achieved school bus length was the following. 9 days after launch, we extended a Tinker Toy-like structure consisting of tens of thousands of piece parts, piece by piece, locking them all into place until 24 minutes later, we had a stiff telescope with which to view the heavens. Mind you, we were never actually able to deploy this fully assembled on the ground. So when the Mars guys talk about their 7 minutes of terror, this was my 24 minutes of terror. But it all worked perfectly, and New Star's been on orbit, making unprecedented images of the high-energy X-ray sky since June of 2012. So making such a huge observational leap means you're going to discover new and exciting things. New Star was able to make the very first high-quality images in high-energy X-rays of the region around the supermassive black hole that resides in the heart of our own Milky Way galaxy. What we discovered was a swarm of dead stars, creating a haze around the supermassive black hole. This haze had never been seen before because we didn't have high enough resolution images in penetrating high-energy X-rays. As you can see, the press picked up on this in an interesting way. So what I'm going to spend the rest of my time telling you about is the fundamentally new things that we're learning about the processes that created the place we live today from the soup of hot hydrogen and helium that existed shortly after the universe was born. Today, 13.8 billion years after the Big Bang, we have a rich mix of chemical elements ranging from the nitrogen in the atmosphere, the calcium in your bones, and the gold in your wedding ring. This movie follows the evolution of the universe as imagined by theorists using supercomputers. Filaments of hydrogen and helium form, shaped by the gravity of dark matter. In these filaments, clouds of dust and gas condense and form stars. The massive ones burn hydrogen and helium to progressively heavier elements like carbon, nitrogen, oxygen, and eventually iron. And finally, these stars run out of nuclear fuel and explode in dramatic events called supernovae. When the universe is older, supernovae explode all over, and as you see in this video, manufacturing elements, spewing them out into the cosmos, where they can condense into galaxies, stars, planets, and life. This movie is based on some governing principles, what scientists think is reasonable, but key components are largely based on theory. How this all works in practice is a dance, a back and forth between theorists and observers with telescopes, including NASA's panchromatic fleet of infrared, optical, X-ray, and gamma-ray missions. So how stars actually explode is a profound mystery. It turns out to be really hard to make a star that's imploding under the force of gravity to explode and expand out into the universe. Stellar explosions have a lot of similarities to atomic bombs, and similar to bombs, huge computational power and theoretical resources have gone into understanding them. But in a huge failure of theory, most computers can't actually make a star explode. What you see here is an example. This is a numerical simulation on a computer of a stellar explosion. We can see here that the explosion halts until an ad hoc mechanism, here the sloshing around of the central part of the star, is put in by theorists to make the star fly apart. This can make the star explode, but is it imagination or is it really what happens in nature? To decide this, we need observations. So previous low-energy X-ray telescopes, like NASA's Chandra mission, have taken pictures of the remnants of supernova explosions hundreds to thousands of years after the event. And like crime scene investigators who look at the shrapnel and other debris to figure out how an explosion happened, astronomical telescopes piece together the workings of the bomb from what's left over, what's still visible long after the event. And as you see here, previous X-ray missions have been able to look at the hot, glowing debris of these explosions, but because of the limited range of colors, they could not see what the heart of the explosion actually looks like. NuSTAR has provided a completely new tool, the ability to look at the radioactive material created in these cosmic bombs. The radioactive embers glow as one chemical element changes into another. Here, titanium is changing into calcium. On cosmic scales, it only glows for a short time, a few hundred years, but the resulting radiation is only visible in the high-energy X-rays, and so NuSTAR can use these to diagnose the nature of the explosion. Here are images of the debris from the historical supernova remnant Cassiopeia A that Ed showed you before in different X-ray colors showing different elements. The red and the green images were made from the low-energy Chandra X-ray telescope, which sees the universe in red and yellow and green colors. NuSTAR has added the blue, the first image in radioactivity. This enables us to see the very heart of the explosion for the first time, and you can see it looks quite different than what you see in red and green. This new evidence is telling us that the shape of the explosion was bubbly, like what you would expect if that sloshing mechanism theorists predicted really happens in life. The crime scene investigators have determined that the sloshing around of the core of this star was key to making it explode. So filling in the pieces of this cosmic puzzle of how we get from an amorphous soup to where we are today. So here's Cassiopeia A in its panchromatic X-ray glory. What made this star explode is understood for the first time thanks to the broad palette of X-ray colors from NASA's suite of high-energy X-ray missions. And next, Neil Garrels is going to tell you about extreme and unusual kinds of cosmic explosions.
Thank you, Fiona. It's a pleasure to be here this evening to talk to you about spectacular explosions called gamma ray bursts and the birth of black holes. And I'd like to start out with a couple of cool movies that we put together. The first one being an atomic bomb explosion that Fiona mentioned. So an H-bomb is the most powerful and destructive explosion that we have here on the Earth. These explosions pale in comparison to that of an exploding star. This is a gamma ray burst with the energy equivalent of 1 to the power 30 H-bombs. That's 1 with 30 zeros after it. Gamma ray burst is a rare type of supernova explosion in which a black hole forms at the center, and they're the most energetic explosions in the universe. I'd like to tell you about the history of gamma ray bursts. They were first discovered by the Vela satellites built at Los Alamos National Laboratories. The Velas were designed to monitor the test ban treaty that the US signed with the Soviet Union to prohibit explosions in outer space. They actually discovered flashes of gamma rays. The first one occurred in 1967. But luckily, it was not a nuclear weapon. It was the discovery of gamma ray bursts. So gamma ray bursts are explosions that are bright flashes of X-rays and gamma rays. They occur about once per day and spread out uniformly across the sky. In the early days, there was no understanding of what could cause these events. In fact, I remember a time when there were more theories, published theories of what could cause a gamma ray burst than there were gamma ray bursts detected. This is one of my favorite ones on the next slide, which was aliens in outer space. This was a newspaper article, Alien Wars. In 1998, an Italian and Dutch satellite made an important discovery that gamma ray bursts were not occurring near the solar system or even in our own galaxy, but were occurring in distant, faraway galaxies. So they're extremely bright events, the brightest events we know of in the sky, in the gamma ray band, but they're occurring far away. So that means that they're incredibly powerful explosions. This is an HST image. You can see the gamma ray burst is the white light and the fuzz is the galaxy in the distance. And so this was really proof that the gamma ray bursts were occurring in distant galaxies. In that same year, 1998, I put together a team of scientists to propose a mission called SWIFT. And we proposed this mission to the NASA Explorer program, which has opportunities every couple of years. There were 40 proposals submitted. Each one is a pretty thick document. I still have the SWIFT proposal in my office. And we were lucky enough to be selected. So with a team of NASA, university, and industry partners, we built this mission in a very fast time, about 4 years from the time we started working on it until we launched it. It was launched in 2004, and it's been working splendidly since that time, even as we speak tonight. SWIFT is a state-of-the-art observatory pushing the frontiers of astrophysics in many different ways. You see on the slide here an ultraviolet image we took with our ultraviolet telescope on board of the nearby galaxy called the LMC. It's a beautiful picture. But I'd like to get back to gamma ray bursts. As of today, we've detected 991 bursts, and we'll celebrate detecting 1,000 bursts in the next couple of weeks. We've simulated what that looks like on this animation of the sky. Each burst is a flash of light, and it's shown on the background of the beautiful image of the gamma ray sky from the Fermi satellite. Every time that SWIFT or Fermi detects a gamma ray burst, we're paged on our cell phones. And scientists get the page and they go running to their computers to see what the universe has sent us and what we can learn about the universe. And I was at a recent gamma ray burst conference when burst went off, and you could see people in the audience slowly filtering out. And then at some point the speaker left, so yeah. You know, this was an event that everybody wanted to look at. One of the things we're learning from SWIFT and Fermi is what's causing gamma ray bursts. When a star explodes, its core collapses to a black hole, and the gas in the region around it in this galaxy flows onto the black hole and disappears forever, as we heard from Jeremy Schnittman. But a small fraction of it gets energized and escapes in jets. We saw beautiful images from HST that Ed showed us. And these jets are what cause gamma ray bursts. It's when the jet is aimed at us that we see a burst. Another important discovery comes from using gamma ray bursts as distant beacons. They're so bright, we can see stars, they're the evidence of stars occurring in the very early universe. It's really the only way we can detect early stars exploding. And we can use gamma ray bursts as tracers to see how many supernovae were occurring in this early part of the universe and how many stars were being formed. These explosions spew material out into space around them. And from them, new stars and new elements are made, and they're spewed out into space. Generation by generation, the abundance of elements evolves until we end up with the mix that we have in our own solar system and that our bodies are made of. We're also learning about the effects of gamma ray bursts on life in the universe. They're so intense that they affect and destroy the atmosphere on planets that are nearby. Luckily for us, this is an extremely rare process, and so the chance of that happening is infinitesimal. It's much less probable than an asteroid causing an extinction on the Earth in the current era. But if we go back several billion years ago, sort of in the middle age of the universe, the material is much closer together, and gamma ray bursts were a major force in preventing life from forming through much of the history of the universe. So on that cheery note, I'm going to end my talk about gamma ray bursts, and we'll turn over to Joan Centrella, who will give us closing remarks. Thank you.
Thank you, Neil. It is a dark, quiet night. You look up and see overhead the Milky Way spreading across the night sky. Surveying the beauty and grandeur of just this one portion of our own galaxy, you are moved to ask some very important and very deep questions. What is this marvelous universe? How big is it? What makes it tick? How did all this come to be? Are we alone in this vast cosmos? Or are there other planets that have life as well? And how do we fit in to all of this? Astrophysics, the study of the universe and how it works, helps us to probe for answers. As we've heard tonight, the beautiful and majestic night sky that we see looking out from the surface of the Earth is just the beginning. Much of the story can only be learned using instruments that are not subject to the limitations imposed by our atmosphere. And so we go out into space with NASA's astrophysics missions such as Fermi, New Star, and Swift. These high-energy missions uncover a dynamic universe, one dramatically different from the tranquil tapestry we see above on a night sky from Earth. By observing cosmic gamma rays and X-rays, these missions reveal that the cold, dark reaches of space are punctuated by turbulent forces, black holes, bursts of radiation, cosmic explosions. Tonight, you have seen and heard about some of these exotic events. You have encountered the most powerful cosmic explosions and the infinite depths of black holes. You've learned that the elements that make up our bodies, the calcium in our bones, the iron in our blood, these elements are produced in the fiery furnaces of stars and hurled out into the cosmos through gigantic explosions. These and other dynamic phenomena have taught us that violent energy is very much a part of the universe. So when we go outside on a clear night, we look up and ask ourselves the great questions of the cosmos. And we know that what we see with our eyes is just the beginning of a marvelous story, a story that is still unfolding, far from finished, and ever more exciting as we explore and observe, question and reflect, discover and learn. Thank you all for coming with us on this marvelous journey, and good night.